Good morning, everyone. This is J. Rakshita from Mechanical Regular. So today I'm going to be taking a lecture on single phase transformer. So these are the topics that I'm going to cover for this lecture. So going to the introduction part. So what are the basic questions that pop up when you say a word transformer? So it obviously would be what is a transformer and why is it needed, right? So here I have given you the questions and also the answers for those questions. So let me read this for you. The first one, what is a transformer? Transformer is a static device by means of which an electrical power is transferred from one AC circuit to another with the desired change in voltage and current without any change in the frequency. So here in this definition, you need to concentrate on two main terms. Okay. So one, that is the transfer of electrical power from one circuit to the other circuit, and the second term is change in voltage and current. Okay, so here coming to the first term, so here we can see the main term, that is AC circuit. Okay, so obviously if we say the word transformer, there is obviously the AC thing that is related to the transformer. Okay, so here in the definition they have mentioned about the circuits. So to understand that better, so I have given you the pictures on the left side of the slide. Okay, so here on the top picture we have the transformer. That is how the transformer looks on the outside. Okay, and coming to the bottom picture, we have the symbolic representation of a transformer. Okay, here the left part of the picture is nothing but the primary circuit, and the right part is the secondary circuit. So how can you differentiate between the primary and secondary? It's very simple. So always the AC supply is connected to the primary circuit, and a load is always connected to the secondary circuit. So that's how you differentiate between those two. And coming to the definition of a transformer. So it is nothing but the transfer of electrical power from one circuit to the other circuit. So here in this case, what are the circuits here? Primary circuit and the secondary circuit. So the transfer of power from primary circuit to the to the secondary circuit with the desired change in voltage. So yeah, coming to this change in voltage, so the change in voltage that which is mentioned in the definition is nothing but that is the basically that defines the need of the transformer. Okay, that provides you the answer for the second question, why is the transformer needed? Okay, basically we have this voltage. What voltage we have in the transformer? Obviously it is a AC voltage. Okay, so what is the advantage of AC voltage? As we all know that AC voltage can be varied. That means it can be lowered or raised according to our needs, according to our requirements. So that is one of the major advantage of AC voltage. And to regulate this voltage or to supervise this voltage, we need a device. So that static device is nothing but a transformer. So this um, pretty much provide you the information of what transformer is and why is it needed, right? Next comes the working principle of single phase transformer. So it works on the principle of mutual induction. This is a very important term, and I'll explain you what mutual induction is with the help of the diagram that I've given you on the side. Okay, on the left side you have the primary circuit, on the right side you have the secondary circuit, and the middle you have the core part. So and coming to what principle is. So yeah, the principle of mutual induction states that when two coils are inductively coupled, and if current in one coil changed uniformly, then an EMF gets induced in the other coil. So what are the two coils that you see in the picture? Primary coil and the secondary coil. So where do the current get generated? In which coil? It will obviously be the primary coil. Why is that so? Because there is the input source that is always connected to the primary coil, hence the current is always generated in the primary coil. And when the current is generated in the primary coil, there is the generation of magnetic flux in the core part. So there you can see the red dotted lines in the core part, right? That is the pathway of the magnetic flux. Okay, so due to this current, the magnetic flux gets generated in the core, and due to this magnetic flux, the EMF gets induced in the secondary coil. So as the principle states, if there is a generation of current in one coil, there would be the generation of induced EMF in the other coil. So that is what the mutual induction is. Okay, if you see this principle, you might have required some other topics that you have studied in your intermediate standards, that is Faraday's law of induction. So this is nothing but the Faraday's law of induction, and this is the working principle of single phase transformer. And going to the next slide, we have Basic paths and losses in transformers. What are the basic paths? Core and the windings. What are the windings? Windings are nothing but the wires. Okay, the wires that surrounds the core. Okay, those are nothing but the windings, or they can also be called as coils. So what is a magnetic core? What is the purpose of a core? Core provides path for the magnetic flux. Okay, as I've told you earlier, the red dotted lines that is traced in the core part. So that is nothing but the pathway of the magnetic flux, right? So it gives you the path, the core provides you the path for the magnetic flux. And due to this magnetic flux that is generated in the core, there are certain losses that are observed, and these losses are called core losses or iron losses. Okay, so these iron losses are mainly classified into two types: hysteresis losses and eddy current losses. So you might have heard of these terms in your previous classes, right? The hysteresis and eddy currents, right? I'll recall you one more time. So what is a hysteresis loss? When there is a magnetic flux that is generated in the core part of the transformer, there would obviously be the magnetic, loops, right? When there is a magnetic loop, there would be a hysteresis loop. I mean, the two terms are somehow related, right? So when there is a hysteresis loop, there is the alternate magnetization and demagnetization happens, and due to this process, there would be the losses during this process. Okay, those losses are termed as hysteresis losses. What are eddy currents? Eddy currents are basically the current loops that are generated due to the varying magnetic field. Obviously, there is a varying magnetic field that is observed in the transformer, right, in the core part of the transformer, and due to that, some part of energy gets lost. So that energy that we lose is termed as eddy current losses. So, and also to minimize these losses, we have various ways or that I have mentioned. So to minimize the hysteresis loss, the core is made up of high grade steel, the magnetic material with high permeability. So to minimize this hysteresis losses, we need to use the magnetic material with high permeability to make the core part. Okay, so here if you take the high grade steel, it has a high permeability, so it can be used to make a core in order to minimize the hysteresis losses. And to minimize the eddy current losses, the core is made up of thin laminations. See, the core, see, if you consider this as one lamination, so on this is one of the thin lamination. Okay, so on combining it with the other lamination, other, you'll form a stack, right? So you'll form a solid stack. So this stack is nothing but the core. So if you combine these thin laminations together, you will get a core. So if you use the thin laminations, then you have a way to minimize this eddy current losses. And coming to the next thing, that are windings or coils. So what are windings? They are wires. So what is the purpose of it? Windings provide the path for the electric current, as we know. And why? What are the materials that constitute a winding? Obviously, it's copper, because for the electric current to travel, there must be a material that has a high conductivity and low resistivity. Okay, so what is the example for of that type of material? Obviously, it's a copper. So the windings are made of copper, and they are wound on the limbs of the magnetic core, as we have discussed earlier. And due to this electric current that is passing through the windings, there are some losses that are observed here also. Those are nothing but the resistive losses or the power losses. So they can also be called as copper losses. Okay, so here to get a better understanding, I have given you this thing. Coming to the types of transformers, we know what are the basic parts of transformers, right? What are they? Core and winding. So based on the arrangement of these two parts, we have the transformers classified into core type and shell type. These are the two main types of transformers. To understand these two transformers better, I have provided you with the pictures at the bottom. So you will get a clear idea of what transformer it is by looking at the pictures. Okay, what is a core type transformer? The core encircles the winding. So we have the core in the middle, and to the core we have the windings. Okay, so the windings are encircles the core. Okay, next, that is the core type transformer. What is shell type transformer? The winding encircles the core. Here in the core type, core encircles the winding. Here in the shell type, winding encircles the core. So if you see the shell type transformer in the picture, so you have two magnetic loops here. But whereas in the core type, you have only one magnetic loop. But here you have more than one. Okay, that is one of the differences between these two. And also, what is the primary differences? Like the winding encircles the core. Okay, if you have the core, if you have the two cores here, like this thing, the core, if you have these two cores, so here in this part, you will have the windings. So the windings encircles the core. So that is basically this shell type transformer. And going to the next slide, we have, so coming to the EMF of the transformer, EMF equation of the transformer. So we have phi is equals to phi m sin omega t. That is a very basic equation we all know. And by Faraday's law, we know EMF is equal to n into d phi by dt on substituting. And by Lenz's law, it becomes opposite, right? Minus gets added. And for the primary winding, we have E1 is equal to minus n1 d phi by dt. So on substituting phi m sin omega t, on differentiating sin omega t, we get cos omega t into omega. And we know omega is equals to 2 pi f. And here we obtain minus cos omega t can be written as sine of omega t minus 90 degrees. So that is taken as equation 1. And psi here is nothing but minus 90. And on comparing this equation 1 and 2, we have EM1 is equal to 2 pi f phi m into N1. So that is a maximum EMF value. And to obtain the RMS value of EMF, you need to divide it by root 2. Maximum EMF by root 2 gives you the RMS value of EMF. So on doing that, you get E1 is equals to 4.445 mF into N1. So that is for the primary circuit. And for the secondary circuit, you got a substitute 1 with the 2, right? E2 is equal to 4.445 mF into N2. The basic difference here is only N1 and N2, right? Number of terms. That is a basic difference between these two. And next comes the, as psi is equals to minus 90, minus here nothing but defines the lagging, okay, lagging state. So even an E2 lags a flux by 90 degrees. So here I have given you the phasor diagram also. And going to the next slide, we have efficiency of a transformer. What efficiency is? Actually, efficiency is nothing but the output power by the input power. And here in the case of transformers, we have input power can be written as output power plus losses. We know the losses, right? What are the losses? Two types of losses: core losses like iron losses and the copper losses. So those are the two main losses. And copper losses are also known as power losses. So for the full load, two conditions we have in the case of efficiency: for full load and for the fractional load. For full load case, we have efficiency is equal to and power, output power, we can write it as V2 I2 cos phi 2 by V2 I2 cos phi 2 plus Wi plus WCU. What are these terms? Wi and WCU. Wi is the iron losses, WCU are the copper losses. The copper losses are also known as power losses, so it can also be written as I2 square R2. So that is the equation, final equation for the efficiency for full load conditions. And for the fractional load, what is a fractional load? So if you take 100% as a full load, then for example, if you consider 100% as a full load condition, then I need to obtain the efficiency for the 60% of it, like 60% of the full load. Then my 60% will be taken as the fractional load. So in the same way, here the fractional load, if we take it as X, then it would be actual load by full load. So which is equals to I2 by I2 in the case of full load condition. So I2 becomes X into I2 FL. So on deriving it and substituting the value of I2 that we obtained in the place of I2 in the efficiency equation, you get the final equation as this. That would be the efficiency of a transformer for fractional load. Next comes the maximum efficiency condition. How you get the maximum efficiency on differentiating it. So what is a variable here? I2, right? So differentiating efficiency with respect to I2, we get the equation, and for the maximum efficiency to obtain, we need to equate the derivative to 0. Okay, so denominator becomes 0, and on simplifying it, you get Wi is equal to I2 square R2. So here Wi are nothing but iron losses, I2 square R2 are nothing but the copper losses. So iron losses and copper losses must be equal. So that is a condition for the maximum efficiency. Only when these two becomes equal, the efficiency becomes maximum. So that is the conclusion of this slide.